Our next speaker is Mher Kazandjian, and his talk is entitled HPC Research Data Management Workflows.
Thank you for the opportunity for presenting my work in the UGM meeting. It's a great honor. Okay, so the title here is a bit different from what you said. I changed it last week. Okay, so this project is about improving data movements in a HPC ecosystem, basically to help users run HPC workflows in an easy way on any HPC machine. And this is part of a innovation zone project at SURF. So when I started working on this, I was told that it's okay to fail, so I went very ambitious. So, these two are typical workflows on that were basically gathered from one or two of the top users of the supercomputer at the Dutch supercomputing facility, Snellius. Basically, a user in like any HPC job, like they have to find their data. In our case, we have a tape archive. So it has to be staged from the tape archive and put like copy to the project space or scratch space on a supercomputer. Then a model runs, and oh, where's the mouse? Oh, okay, good. Basically, they produce some data, and then in the second workflow, they take that data, do some processing with it, and if they find that there's a problem, they run it back in the first workflow. So it looks a bit complicated. And one of the main complaints of these users were that people involved in this project are spending too much time just like juggling the data and like finding the data. So that's one of the reasons why this project exists. So they reported that they spent like 30% of their time just on the data management part. So our goal is basically to bring this to zero. And for some context, like one FTE full-time employment in Holland costs around 200,000 euros. So if you're spending 30% of that just moving data, dealing with the data management part, that's around 6,000 euros per person. And when translated to CPU hours, that's around 3 million CPU hours. So which is like a huge amount of compute. Okay, so on the supercomputer of Surf, so there are several types of storage systems. So there's the home partition, there's the project space, and of course there's the tape archive. And some of the compute nodes have local NVMEs. We call them scratch node. And basically, users should be able to move data across these tiers in an easy way. Uh, like any data movement operation, you have to do lots of like CP, MV, MKDIR, sync, rsync, SCP. And if you have a tape archive on top of that, you have to do like staging commands, like we call them like data archive get and so on. In the previous talk, like users are already terrified from terminals. So you have to deal with it one way or another. We started thinking like how can we hide complexity from the users? So we decided to give it a shot with iRods, but also like put a wrapper around iRods, not ask users to go from using CP and rsync to use like the I command. While developing the package, it's written in Python. It changed a bunch of times. So we settled to Flow, and the Flow is fast. I have a background in HPC, so I focused a lot on the performance part. Basically, we managed to achieve throughputs of more than 10 gigabytes per second. Yeah. So how did we hide the complexity from the user? So for that, we need to develop the basic building blocks. And since it's a uh, um, uh, like since it's a uh, like innovation, like R&D project, so we wanted to dream big, and we thought that why don't we develop a wrapper using iRods to federate multiple sites together in an HPC setting. So the main challenges here is that if you want to do something like this, especially if you want to do it with iRods, like you have to worry about the high ports, and that's a nightmare for IT for the like enterprise IT part, because they will ask a billion of questions like, why do you need this range of ports? Why do you need this many ports, and so on. And every site has its own different configurations. So we thought that why don't we deploy iRods on a supercomputer as a user, like not as an admin? And this was the difficult part, but it was also lots of fun. And the disclaimer, so the first half of this was done without Claude. The second half was done with Claude. So the deployment of iRods, like with Postgres and the iRods server, was done in the first 6 months. So basically, the first step is that you want to run iRods somehow uh, on a compute node. And we settled, not settled, I mean, the best choice for this is Aptainer, because you typically on supercomputers, it's available. And yeah, and it's quite easy to use. So first we tried that. So basically, the first attempt was to put iRods and Postgres in on one compute node. And basically, first we developed the definition file. And the problems that we solved here was we had to patch the iRods installer because it uses the Chown and the El Chown like OS, like Python modules. And also one challenge was that we had to build the images on a VM and then push it to the compute node. But that's something you do just once. And for the Postgres part, it's easy because you can run Postgres as a unprivileged user. And one can say like, but yeah, but you don't have systemd. How do you do it? So we did it with the supervisory. Okay. So some small screenshots on how things work, like before wrapping things up, just to test the waters on how things would look like. So this is the Aptainer command to launch the service, like the iRods and Postgres container. So this looks ugly. You don't want to show this to any user. So uh, okay. So just running the who am I command. Yeah, it works. And also like showing the just running ILS, it lists the what's there. Of course, initially it's empty, so it will not. So there's nothing to see there. But at least it works. It doesn't add around. Okay, so the second challenge is that to run this, so here we were running it on one node. Now we want to run it on multiple nodes. So it's the same procedure. So this is where Claude came in. So basically we uh, updated the package to understand Slurm. And basically when a job is launched, it fetches everything from the environment and it spins up. Of course, you need to have one ICAF. And on every compute node that you have, you will have a resource server there. And it will automatically register the storage available on these nodes as resources in iRods. Yeah, okay. So basically, for every site that you want to deploy this on, you need to develop a configuration for flow. And this is the minimal configuration that you can have. You just say that this is the name of my project, and these are the servers that I need. So this is for like one compute node. And if you want to have like multiple compute nodes, you will have your ICAT, your resource, and your resource servers. So when you submit this with Slurm, these are Jinja templated, and it just spins up like adds as many blocks as needed. Okay, so this is a little bit busy diagram, but it shows how the storage is laid out on Snellius, the supercomputer, and one of the problems that we wanted to tackle is basically if you have a data set in the archive and you want to broadcast it to the local disks on the compute nodes. So these are these local NVMEs, so scratch node, scratch node, scratch node. And each one of these has 4 gigabytes per second read-write, approximately. So when you spin up the solution, basically it discovers the configuration file automatically, and you can specify how many compute nodes you need. So you run this on the compute node, it's on the head node. And if you put here like 4 or 8, it will just submit the jobs and they will all connect together. So in this example here, I use 2 compute nodes, and when it spins up, basically you have the ICAT on one node and the 2 resource servers on the other 2 compute nodes. And as it spins up, it does all the health checks, and so this runs in the foreground on the head node. Okay, so let's see it in action. So an LS, yes, it lists what's in there. And if you want to see your resources, we called it stores, just to keep it generic. Because this backend, it is for now it's IRODS, but we want to have it generic to plug anything else if you want in the future. Okay, so if you list the stores, the resources basically. So you have a archive resource on every compute node. You get your home resource. So you have like a home here, a home here, and a home here. And also by default, it includes the RAM disk as a resource as well, and the local NVMEs, plus the shared storages. Okay, so like a put 1 gigabyte file, done, like around 1 gigabyte per second. You list it and then you get it, all good. So this was basically the difficult part, like having IRODS work in a persistent and a robust way on through Slurm. Yeah. Okay. So in order to make things easy, because if you have, let's say, a data set on the archive and you want to broadcast it to the local NVMEs on the compute nodes, so users can use this wrapper. So this is not targeted for like new users or entry-level users. So this is targeted to a little bit of a power user who likes to experiment, let's say, and be a bit adventurous. So in this case, we're broadcasting one data set, like the same file is broadcasted to all the compute nodes. In the first, here we implemented the MPI. I mean, like if you're familiar with MPI, so basically a broadcast, it just puts it's like a iREPL. But we did it in an efficient way. So basically, in the first round, it copies the file using iREPL to the two compute nodes, and from there, each one copies it in turn to 2 other compute nodes. So here in this case, this was done on 8 compute nodes, and like effectively, once the transfer is complete, you're transferring, like you're doing a copy of you're doing the copy at around 13 gigabytes per second, like effectively, like this is the aggregated throughput. And we implemented a sidecar for IRODS for direct memory access over InfiniBand. So basically, what this does is that it uses RDMA to copy the data, to transfer the data from one place to another, and then it does an IREG with IRODS to register the file. Okay, So the next goal was to federate two sites together. At Surf, there's an experimental platform. It's called Lisa. It has like FPGAs, fancy GPUs, accelerators, and so on. And this is the supercomputer here. And I can SSH from one to the other, but I assume that I cannot SSH from one to the other. I configured them to talk to each other through SSH tunnels through a server in the cloud. And so basically, both of these can SSH to this server in the cloud. And the flow basically sets up all the forward and the reverse SSH tunnels. And yeah, this was like amazing to see to work. So, so basically, so once the process is launched, you can list from files from like across zones. So you can so metadata reads are done seamlessly. So here, this is a listing of content on the supercomputer, and this listing is the command to list the metadata, content on the experimental platform. And here, basically, you're listing the zones, and when you list the zone, it shows that Snellius is the local zone and Lisa is the remote zone. Okay, yes, so I forgot to mention that, and now work in progress is to federate Lumi, like it's the pre-exascale supercomputer of Europe in Finland. Okay, coming back to this slide, how to reach the 0% effort on data management. So a lot of presentations and talks here, like mentioned some things that can contribute to that. And I think one of the most important thing is that there should be a top-down effort, like from management, to encourage and invest more in data management. And of course, awareness and training is very important. And since there was this discussion about using AI, and now apparently like everyone is using AI, so I started experimenting with an MCP server that can talk to Claude. But it could, so since it talks the MCP protocol, you can just hook it to any harness that you have. It works well, but it's still like, it was like a 1 or 2 day of work. So I'm also experimenting with the terminal user interface that, for example, if you, that helps with findability. So if you want to list your content, it's on the terminal, like you just launch it. So in this case, it's like HPC RDM flow browse, and it opens like a terminal user interface, and you can just live update, search your data, and it filters on the fly. It's very fast. So unfortunately, I don't have a screenshot of that yet. So yeah, our goal is to include like at least 3 or 4 more zones here in this experiment. Because what one can do basically is that you can, since this is an experimental platform, let's say you develop some code on a GPU here, and you run it on a bigger system that has more GPU resources. So in this case, on this cluster, there's one fancy GPU. So you develop and test your code here. Then you run a bigger benchmark on the supercomputer that has around like 400 or 500 H100 GPUs. And here on Lumi, you have like, I think around 10, 20,000 GPUs. They could be 40,000, but I'm not sure. Yeah, so all these like transfers could be done in a very easy way instead of worrying like, hey, how can I SSH, SCP, put the keys here, there. Okay, so yeah, so thank you, and that's it.
Do we have any questions? Got one right here.
So I saw that Lumi was soon. Is that because you already have access and you're going to be doing this test, or you're waiting for access?
No, I do have access, but on Lumi they use Singularity. They don't use Obtainer.
Right.
So and they have different options for like, for example, with on Snellius they have like some default mounts that are hard coded like in ITSI, Obtainer, blah blah. So on Lumi they have Singularity, and they have harder constraints because you cannot So once you have a job, you cannot SSH to the compute node.
That's right.
So I'm exploring that. So
And are you working with anyone at those places, or is there anybody else doing this, or is
no,
it
no, it's
just
just me.
you?
It's
Yeah,
just me and Claude.
Yeah.
So.
that's right. You and Claude, yes. Excellent. Thanks.
Okay, a question from Slack. Have you considered using a configuration management tool like Ansible to deploy iRods instead of deploying it through Slurm?
Yes, I think it's mentioned in one of the slides at the bottom. Yes, so once the Slurm job launches, first time configuration is done with Ansible in background. Yes, the answer is yes. And
Okay.
and this works in a persistent way. So let's say you launch another job, you can retrieve like so the Postgres database is preserved. So I mean you can delete it if you want to, but
All right. Thank you.